Welcome back to The Explainer. Today, we're diving straight into a massive bottleneck in computational materials engineering. When it comes to designing cutting-edge aerospace structures or advanced automotive parts, woven composite materials are absolutely invaluable. But predicting exactly how these incredibly complex materials are going to bend, stretch, and yield under stress, that is a gigantic computational headache. Modeling the physics at a microscopic scale requires just an immense amount of computing power. Think of it like trying to render a blockbuster CGI movie frame by frame on an old home laptop. It takes forever, and it makes rapid engineering innovation really, really difficult. So today, we're looking at a fascinating technical solution to this exact problem, a brand new framework for multi-fidelity data fusion. Our foundation for this explainer is a 2025 paper by Gane, Fagerstrom, and Merkaloff, published in Composites, Science and Technology, and they are tackling this bottleneck head-on. We already know that surrogate deep learning models, specifically neural networks, can give us a super fast, efficient way to predict material behavior. But there's a pretty big catch. Neural networks are incredibly data hungry. They need massive datasets to actually learn the underlying physics. So the core mission of this research is to bypass that limitation by brilliantly combining highly accessible, low-accuracy data with very scarce, high-accuracy data. Here is our roadmap for today. We'll hit 1. Modeling inelastic woven composites. 2. Two-step homogenization and FFT. 3. Temporal correlations in data. 4. Multi-fidelity transfer learning. And finally, 5. Validating the surrogate model. Let's get right into it. Section 1. Modeling inelastic woven composites, the computational challenge. Okay, so woven composites consist of yarns interlaced in those classic over and under patterns, right? The warp and the weft, all embedded in a resin matrix. When you apply extreme stress to these materials, that matrix exhibits elasto-plasticity. Basically, the material deforms permanently, and its current physical state depends completely on the history of the load applied to it. In engineering, we call this path-dependent behavior. And simulating this path-dependent plasticity using traditional finite element analysis, it is so computationally expensive. It simply takes way too long to be practical for fast-paced engineering. So we need neural networks to act as rapid stand-ins, or surrogates. But that brings us back to the main problem. How do we get enough data to teach the neural network the physics without running those insanely expensive simulations for years? Moving right along to Section 2, two-step homogenization and FFT, generating the data. Take a look at this structure. This is the meso-scale representative volume element, or RVE, of the woven composite. To generate high-fidelity, accurate data, you have to digitally construct this physical structure. The researchers used a highly detailed 64 by 64 by 64 voxel-based mesh to explicitly model the weave pattern, the yarn spacing, the crimp, the whole shebang. This explicit geometrical modeling is exactly what gives the simulation its high fidelity. It's mathematically incredibly close to reality. Now, this graph perfectly illustrates the contrast we're dealing with. It compares 3 different ways of simulating how that woven geometry handles stress. Check out the dotted green line. That's mean field homogenization, or MFH. It uses the two-step mathematical averaging procedure. It's lightning fast, taking just 30 seconds to run. But as you can plainly see, it deviates a lot from reality under complex cyclic loads. So that's our low-fidelity data. The solid red line? That's the traditional finite element method. Highly accurate but painfully slow, over 7,000 seconds per simulation. But then, look at the black dashed line. That represents the fast Fourier transform, or FFT homogenization. By converting this spatial topology into the frequency domain, FFT gets results almost identical to the highly accurate finite element method, but in a fraction of the time. So FFT provides our precious high-fidelity benchmark data. All right, Section 3, temporal correlations in data, processing time series stress. So the big takeaway here is that stress responses in these inelastic materials are not just isolated static data points. You have to treat them as multivariate time series data. And the reason comes down to physics. Because of that path-dependent plasticity we talked about, the stress state of the material at, say, time step 50 is directly linked to what happened to it at time steps 48 and 49. In fact, the researchers proved through autocorrelation analysis that these temporal correlations stretch up to 10 time increments into the past. So whatever neural network you choose for this task, it absolutely has to have a memory. Specifically, the team went with a gated recurrent unit, or GRU network, because it totally excels at handling time-correlated sequential data. But dealing with time series data from simulations creates a massive formatting problem. The high-fidelity FFT simulations naturally converge at entirely different speeds. So you might get time series data that's 15 steps long for one simulation and 100 steps long for another. You literally cannot train a structured GRU network on wildly uneven data like that. To fix this, the researchers used a really clever data augmentation technique. They identified the varying lengths of the FFT data and simply applied linear interpolation to stretch and standardize all of them to a uniform 101 time increments. This didn't just solve the formatting nightmare, it actually enriched the temporal correlations without requiring a single extra second of expensive simulation time. Which brings us to Section 4, Multi-fidelity Transfer Learning, Bridging the Gap. The architecture of this transfer learning framework is super elegant, and it's executed in specific steps. Instead of training the neural network from scratch using only the tiny amount of high-fidelity data they had, they built its knowledge incrementally. In Step 1, they pre-trained the GRU network on a massive dataset of 28,000 fast, low-fidelity MFH samples. Basically, the network learns the general rules of physics here. Then, in Step 2, they take those pre-learned weights and fine-tune the whole network using a much smaller batch of just 1,000 high-fidelity FFT samples. Step 3 exposes the model to really specific, tricky conditions, like pure shear cyclic loading, to dial in the accuracy. And finally, Step 4 evaluates the fully trained model against totally unseen benchmark simulations. Let's see how it actually performed. Section 5, Validating the Surrogate Model, Empirical Results. This right here is the ultimate test. These graphs represent completely unseen, highly complex, random walk strain paths. The solid lines, black, red, and green, are the true high-fidelity FFT target stresses. The dashed lines are the predictions generated by our newly trained GRU surrogate network. Look closely at how those dashed lines lock almost perfectly onto the solid lines across all 6 stress components. It's seriously impressive. The network successfully took the general knowledge from the low-fidelity data and adapted it seamlessly to the high-fidelity physics. But they didn't just stop there. They pushed the model to its absolute limits by testing it on highly sparse data, like cyclic pure shear loading, where most of the input parameters are just 0. On the left side of this figure, you're looking at a model trained from scratch on the original short-length time series data, and you can see it really struggles to capture those stress peaks accurately. But check out the right side. This is the model trained on the augmented cyclic FFT dataset, where they applied that linear interpolation technique we discussed. That augmentation allowed the GRU network to deeply understand the path-dependent plasticity, giving us predictions that track the complex physical reality with just remarkable accuracy. Honestly, this graph is probably the most crucial takeaway for practical real-world engineering. It plots the prediction error against the size of the training dataset. The red line is a neural network trained from scratch. The green line is our multi-fidelity transfer learning model. Focus your attention on the left side of the graph, where training set sizes are super small, like 50 to 100 samples. Remember, generating high-fidelity data is wildly expensive, so these small training sets are the harsh reality of materials science. Notice how the green transfer learning model just decisively outperforms the model trained from scratch? It has significantly lower error rates and a much tighter standard deviation. It's definitive proof that learning from abundant low-fidelity data gives you a massive advantage when high-fidelity data is scarce. So, as we wrap up, I want to leave you with this thought. By successfully overcoming the data-hungry limitations of neural networks, we literally no longer need thousands of hours of supercomputer time just to map out every single variation of a composite material. How is this multi-fidelity data fusion framework going to accelerate the discovery and modeling of complex future materials? It completely opens the door to rapid prototyping and digital testing on a scale that was practically impossible before. We are looking at a fundamental paradigm shift in computational materials engineering. Thanks for tuning in to this explainer to explore this amazing research. The rigorous methodology and the results we discussed today are all thanks to the dedicated work of the researchers at the University of Gothenburg and Chalmers University of Technology. If you want more insights into the mechanics and physics of advanced composites, definitely go check out their ongoing projects over at materialslab.org. Keep exploring the science, and I'll catch you in the next explainer.